Welcome back to our series on electricity and magnetism. In this particular episode, we're going to continue our electric field from a charge distribution, except this time we're going to look at charge along a circular arc. The circular arc we're going to choose is actually the first quadrant of the coordinate system. So we're going to lay charge along a circular arc of radius r. So this will be the radius, and the charge will be laid along a line that runs along a circular arc with that consistent radius. Of course, this is the x and the y-axis. One of the things that will make this problem a little different from the previous one is, of course, this will produce a two-dimensional electric field. I know that if this is a positive charge distribution and I'm interested in finding the electric field at the origin as a result of it, well, there will be an electric field vector that fundamentally points in that direction. If this is a uniform distribution, it should actually point 45 degrees into the third quadrant. But that's going to mean it's going to have both x and y coordinates. And we didn't have to worry about that in the previous example because it was just one-dimensional. The field lay entirely on the x-axis. I'll show you how we're going to handle that idea that we're going to have a two-dimensional electric field. First, though, let's run through the same litany we had to for the last problem. First, we have to define the charge distribution so that I can get a quantity related to the geometry of the problem for dq. In this case, we're going to lay q all along the arc length, which I'll call s. This is the arc length that runs from here all the way down to here, and it's got an amount q laid entirely along that length. That, of course, is equal to lambda because it's still the linear charge distribution. It has no thickness. Well, in this case, that's equal to dq, the tiny amount of charge in this particular little element I'm going to select. Its denominator, though, is more complex than last time. It certainly doesn't lie on the x-axis or the y-axis. It actually lays along an arc length. And if you remember from your Algebra 2, the length of an arc can be expressed in terms of the width of an angle. The angle we're going to use is theta. So we're going to move along theta in order to actually define the width of that little piece of arc. The arc width isn't just a function of theta, it's also a function of the radius. Think about the formula for circumference. It's 2 pi r. So in addition to being a full circle, the radius multiplies to indicate how large a circle it is. So this denominator is actually r d theta. Okay, now I have a relationship between dq and the geometry of this problem. It's going to be lambda r d theta. Okay, the next thing I need to do is define the radius because I'm going to need that for the denominator of my integral calculation. Fortunately, in this case, it's a consistent radius. It doesn't change at all. The radius is r for every single piece of the integral. So r equals r. No change necessary. And the final piece is pretty easy too. If I want to integrate along d theta, I just need two angles. The angle that represents one limit and the other one. And I think everybody can see that's going to be between 0 and pi over 2. So I'm actually ready to write my integral. The integral in this case is going to be that dE is going to be equal to k dq over r squared. And for this particular problem, that's going to be k times r lambda d theta divided by r squared. And my limits of integration are going to be between 0 and 2 pi. So E is actually going to be equal to the integral from 0 to pi over 2 times k r lambda d theta over r squared. Of course, the r and r squared can cancel, but what's most important in this one is that everything's a constant except for d theta. K doesn't change, the radius doesn't change, the lambda doesn't change because it's just a ratio of the distribution. So it's literally just going to be an integral of d theta. In this case, for an arc, in the plane of the arc, finding the electric field in that plane is really easy. But now we have to consider the two-dimensionality of this. That is, there's really no such thing as a single vector. That vector points in this direction, but there's nothing about this magnitude that's going to give it to me because it doesn't take into account that some of that vector electric field points along the x direction and some points along the y direction. and I need to take both into account. So what we're going to do before we rewrite this is draw in the two vectors we're actually finding. I'm finding Ex, which is the amount of the electric field produced by this arc of charge that points horizontally, and Ey, which is the amount of the electric field produced by this charge distribution that points vertically. And of course, theta is going to be our guide. As we move along the theta, the size of these components are going to differ. Basically, when I take this particular component right there, the theta value that points to it will tell me how much of this contributes to both the x and the y vector, and I'll have to use some right triangle trigonometry for that. Of course, I know that the x component of any vector is always cosine theta times the magnitude of the vector. So that's what I'm going to use to write this set of vector integrals. The overall E is really going to be a function of two different integrals. My first integral is the integral from 0 to pi over 2 of kr lambda d theta divided by r squared, but that's going to be times the cosine of theta, and that of course is going to all be in the I hat direction. I hat being just a representative of any vector that lies along the x-axis. In addition, I'm going to have to do a second integral, one for the y direction, and of course that's going to need a cosine. So it'll be the integral from 0 to pi over 2 of kr lambda d theta over r squared, and this will be times the sine of theta, and that of course is going to be in the j hat direction, in the y direction. Once again, these integrals do a great job at telling me the magnitude, but they don't do a very good job at telling me the direction. So I'll add those on myself. I know at the end, the x component is going to point negatively, and so is the y. So I'll make sure that's what they value at the end. Okay, well, these two integrals are the same, other than one's got a sine and the other one has a cosine. And of course, those are both functions of theta, so they can't come out. But I can take a bunch else out of here. First, I can take out the kr, the lambda, and the r squared. So it's going to be k lambda over r, and then that's times this whole thing. And let's go ahead and perform these integrals while we move across. The integral of cosine is simply sine. So this will be sine theta evaluated between 0 and pi over 2. And then plus, and I'll have the same thing over here. I've already taken out the k, the lambda, and the r, so this is simply going to be, the integral of sine is negative cosine, so this would be negative cosine theta evaluated between 0 and pi over 2. Okay, well now we're ready to evaluate these two parts. It's going to be k, oh, excuse me, I got to add back in the directions. This of course is in the I hat direction, and this of course is in the j hat direction. Okay, so we've got k lambda over r. In the I hat direction, again, sine of pi over 2 is 1, sine of 0 is 0, so this just produces 1. So this is going to be I hat. For the second one, again, the cosine of pi over 2 is 0, the cosine of 0 is 1, and it's minus, so this is simply going to produce j hat. So there's the magnitude, and it even indicates that it's this amount along both the x and the y direction. Of course, that means along the actual diagonal that's the sum of the two, we'd be considering a special right triangle that's a 45, 45, 90. It has the ratio of sides 1 to 1 to radical 2. So I could actually put these together and simply describe the overall vector. The vector that points down in the third quadrant is actually going to be, this would be E total, and if we can draw it in, it'll look like this, E total. It will actually have a magnitude of the square root of 2 times k lambda over r. But we could also leave it in this formation right here. Again, this guy is going to point in the third quadrant, and the only way to make these point in the third quadrant is to make them both negative. So this is also equal to negative k lambda over r times I hat plus j hat. The negative in front will make both these vectors negative, and that means it will point in the third quadrant. Both of these represent the same answer to the same question. This gives it as a single vector. It has to reference, however, that it points in the third quadrant, and this one actually points in the correct directions along the x and y direction. So that is the way we calculate an electric field for a circular arc. Note, if the arc gets longer and encompasses a semicircle, really the only change you have to make is now your integral has to run from 0 to pi. If it runs a full circle, of course, the electric field at the center will be 0 because it'll have a repulsive electric field vectors pointing from every direction, and symmetry will guarantee that they cancel. Let's talk symmetry for just a second. There actually is maybe a different way to envision this problem. That is, if all I'm after is the magnitude of the vector, because I already know the direction it points midway through the third quadrant. An easier way to actually calculate its magnitude might have been to perform a transformation. That is to rewrite our x and y axis so they look like this. Because notice what happens. If I rewrite the x and y axis so that it places this arc straddling the x-axis, I know that the y component of such a distribution will cancel because half of the arc is forcing it down and the other half is forcing it up. They're equal and opposite. So if I redrew it or reconfigured it that way, all I would have needed to do was calculate just a single component along the x direction. So consider that whenever you look to calculate these charge distributions, frequently relocating the axis in comparison to the problem will actually give you an opportunity to solve it even easier. Well, in both the examples we did, we were lying within the same plane of the charge distribution. That is, we were at the origin while the charge distribution was within the plane of the board. What happens if the charge distribution and where we're locating it goes into 3 dimensions? Well, the calculus of that can get very complicated. And we're actually going to look at one of those, basically a full ring, and then we're going to look at the axis of the ring coming out. We'll look at the electric field along that line.